Hello students, welcome to this video. In this video, we will solve question number 101 to 110 of binomial theorem. So the link to download the PDF will be in description, as well as at the end I will show you how you can download the PDF copies of other books as well. Also, I will show you my question answer website where you can come and ask questions related to mathematics, because YouTube comment is not really suitable for asking questions of mathematical nature. So without further ado, let's get started. Question 101 says that we have to show that C0 upon 1 minus C1 upon 5 plus C2 upon 9 and so on up to minus 1 to the power n, Cn upon 4n plus 1 is equal to n times 4 to the power n upon 1 times 5 times 9 and so on up to 4n plus 1. So we know that the expansion of 1 minus x to the power n is C0 minus C1x plus C2x square up to minus 1 to the power n Cn xn. We substitute x is equal to x to the power 4, we get 1 minus x4 to the power n is equal to C0 minus C1 x to the power 4 plus C2 x to the power 8 and so on up to minus 1 to the power n Cn x to the power 4n plus 1. We integrate within the limits 0 to 1. So our left hand side is C0x minus C1 x to the power 5 upon 5 plus C2 x to the power 9 upon 9 and so on up to minus 1 to the power n Cn x to the power 4n plus 1 upon 4n plus 1. And right hand side is the integration of 1 minus x to the power 4 to the power n. We integrate it by parts, right hand side, that is, this should be 0 to 1 actually, not 0 to 1. Upon integrating by parts, we get x times 1 minus x to the power 4 to the power n within limits 0 to 1, and then minus x times n 1 minus x to the power 4 and minus 1 minus 4x cubed dx. So we have minus 4 and we take out, and we are left with integration within limits 0 to 1, 1 minus x to the power 4 to the power n minus 1, 1 minus x to the power 4 minus 1 dx, which is equal to minus 4n in plus 4n in minus 1, that is in upon in minus 1 is equal to 4n upon 4n plus 1. So in upon I0 becomes eventually in by in minus 1 times in minus 1 upon in minus 1 and so on up to I1 upon I0. So you substitute the values, you get it equal to 4 to the power n times n factorial upon 5 times 9 up to 4n plus 1. The other solution could be, we put x square is equal to sine theta, so 2x dx is equal to cos theta d theta, and dx becomes cos theta d theta upon square root of sine theta. When theta, x is equal to 0, theta is equal to 0. When x is equal to 1, theta is equal to pi by 2. So our integration becomes 0 to pi by 2 cos to the power 2n plus 1 theta d theta upon 2 square root of sine theta. We take out cos to the power 2n theta separate, it becomes cos theta d theta upon 2 square root of sine theta. Now again we integrate by parts, you get cos to the power 2n theta times square root of sine theta between limits 0 to pi by 2 minus 2n cos to the power 2n minus 1 theta minus sine theta into square root of sine theta d theta. So this is 0, and this integration becomes 2n between integration 0 to pi by 2 cos to the power 2n minus 1 theta into sine square theta upon square root of sine theta d theta, which becomes 0 to pi by 2 cos 2n minus 2 theta. Sine square theta becomes 1 minus cos square theta, and this we treat as this part becomes cos theta upon 2 square root of sine theta d theta. And we eventually land up at the same recurrence relationship, that is 4 in minus 1 minus 4n in, that is in upon in minus 1 is equal to 4n upon 4n plus 1. And then we proceed like we have already done. Question 102 says that we have to prove that C0 upon n minus C1 upon n plus 1 plus C2 upon n plus 2 and so on up to minus 1 to the power n Cn upon 2n is equal to n factorial times n minus 1 factorial upon 2n factorial. So we have 1 minus x to the power n is equal to C0 minus C1x plus C2x square up to Cn and x to the power n. There should be minus 1 to the power n here. Now we multiply both sides by x to the power n minus 1. We get x to the power n minus 1 times 1 minus x to the power n is equal to C0 x to the power n minus 1 minus C1 x to the power n plus C2 x to the power n plus 1 and so on up to minus 1 to the power n Cn x to the power p1 minus 1. We integrate within limits 0 to 1. Left hand side becomes integration within limits 0 to 1 x to the power n minus 1 1 minus x to the power n dx. And right hand side gives us the form of left hand side C0 x to the power n upon n minus C1 x to the power n plus 1 and upon n plus 1 C2 times x to the power n plus 2 upon n plus 2 and so on within limits 0 and 1. So again, when we take the limit, this right hand side becomes our left hand side equal to left hand side of the question, and right hand side becomes 0 to 1 x to the power n minus 1 1 minus x to the power n dx. So we integrate it by parts. The first part becomes x to the power n minus 1 1 minus x to the power n plus 1 upon minus n plus 1 0 to 1. And the second part becomes 0 to 1 n minus 1 x to the power n minus 2 1 minus x to the power n plus 1 upon minus n plus 1 dx. So this becomes minus n plus n minus 1 upon n plus 1 integration 0 to 1 x to the power n minus 1 1 minus x to the power n plus 1 dx. That is equal to n minus 1 upon n plus 1 in minus 2 comma n plus 1. And then we establish the recurrence relationship. There is some typing mistake here. Okay, there should be a sign of integration here. So eventually it becomes n factorial times n minus 1 factorial upon 2n factorial, as we can observe in this recurrence relationship. Question 103 says that we have to prove that C0 upon n times n plus 1 minus C1 times n plus 1 times n plus 2 plus C2 upon n plus 2 times n plus 3 and so on up to minus 1 to the power n Cn upon 2n times 2n plus 1 is equal to 1 upon 2n plus 1 times 1 upon 2n C and minus 1. So we write this as C0 upon n minus C0 upon n plus 1 minus C1 upon n plus 1 minus C1 upon n plus 2 and so on up to minus 1 to the power n Cn upon 2n minus Cn upon 2n plus 1. So we write this as C0 upon n minus C1 upon n plus 1. We take this term and then we write C2 upon n plus 2 and so on up to minus 1 to the power Cn upon 2n minus C0 upon n plus 1 minus C1 upon n plus 2 and so on up to minus 1 to the power n Cn upon 2n plus 2. And then this becomes a problem similar to 102 and we proceed similarly to arrive at the answer. Question 104 says that prove that C0 upon k minus C1 upon k plus 1 plus C2 upon k plus 2 and so on up to minus 1 to the power n Cn upon k plus 1 is equal to n factorial upon k into k plus 1 and so on up to k plus n. If you look carefully, this question 104 is similar to 102 and we solve similarly and you will arrive at the answer. So similar recurrence relationship has been found for question 104. Question 105 says that show that C0 square minus C1 square plus C2 square minus and so on up to minus 1 to the power n Cn square is equal to 0 or minus 1 to the power n upon n by 2 times n factorial upon 2 whole square according as n is odd or even. So we know that 1 minus x to the power n is equal to C0 minus C1x plus C2x square up to minus 1 to the power Cnx to the power n. And x plus 1 is equal to C0 x to the power n plus C1 x to the power n minus 1 and so on. We multiply both the equations, we get this is equal to 1 minus x square to the power n. Now coefficient of x to the power n on left hand side is c0 square minus c1 square plus c2 square up to minus 1 to the power n cm square. Right hand side is c0 minus c1x square plus c2x to the power 4 and so on. We observe that powers of x are even on right hand side, and so if n is odd, then coefficient is 0. If n is even, then coefficient of x to the power n on right hand side is minus 1 to the power n upon 2 cn by 2. That is minus 1 to the power n upon 2 n factorial upon n factorial 2 whole square. Question 106 says that show that MCR times C0 plus MCR minus 1 times MC1. This should be MCR. This should be M. And this should be MC0. This is MCR, MC0. And MCR minus 1 times MC1 plus MCR minus 2, MC2, and so on up to MC0, MCR is equal to M plus N CR, where M and R are positive integers and R less than N, R less than N. So we have 1 plus x to the power n is equal to nc0 plus nc1 plus nc2 x square, and so on up to ncn x to the power n. The moving terms are written something like ncr minus 1 x to the power r minus 1 plus ncr x to the power r. And 1 plus x to the power n is mc0 plus mc1 plus mc2 x square, and so on mcr minus 1 x to the power r minus 1 plus mcr x to the power r, and so on up to mcm x to the power m. We multiply both and equate the quotient of x to the power r. We get mcr times mc0 plus mcr minus 1 mc1 plus mcr minus 2 mc2, and so on up to mc0 and cr is equal to m plus n cr. Question 107 says that we have to prove that 2nc0 square, 2nc1 square plus 2nc2 square, and so on up to minus 1 to the power 2n times 2nc2n square is equal to minus 1 to the power n 2ncm. So 1 minus x to the power 2n is 2nc0 minus c1 to 2nc1 x plus 2nc2 x square, and so on up to minus 1 to the power 2n c2n square, c2n c2n. This n is at wrong place, and x plus 1 to the power 2n is equal to 2nc0 x to the power 2n, the same series in decreasing fashion. We multiply both of them and equate the quotient of 2n. We get 2nc0 square minus 2nc1 square, and so on up to minus 1 to the power 2n. 2nc2n square is equal to minus 1 to the power n 2ncn. Question 108 says that show that c1 square plus 2c2 square plus 3c3 square up to ncn square is equal to 2n minus 1 factorial upon n minus 1 factorial square. So 1 plus x to the power n is c0 plus c1x plus c2x square up to cnxn. We differentiate both sides with respect to x. We get n times 1 plus x to the power n minus 1 is equal to c1 plus 2c2x plus c3x square, and so on up to ncn x to the power n minus 1, and x plus 1 to the power n is c0x to the power n plus c1x to the power n minus 1 plus c2x to the power n minus 2 and up to cn. We multiply both the equations to get n times 1 plus x to the power 2n minus 1, and this is that series both multiplied, both the series multiplied. We equate the quotient of x to the power n minus 1, and we have c1 square plus 2c2 square plus 3 times c3 square, and so on, and we find the quotient of x to the power n minus 1 in this, which is equal to 2n minus 1 factorial upon n minus 1 factorial square. So this one would be 2n minus 1 c n minus 1. So this n will cancel 1n in the denominator. Sorry. Let me get rid of this. Question 109 says that show that c0 square plus c1 square by 2 plus c2 square by 3 plus up to cn square by n plus 1 is equal to 2n plus 1 factorial upon n plus 1 factorial whole square. So similar to previous question, we write the expansion of 1 plus x to the power n and integrate with any limits 0 to 1 to arrive at 1 plus x to the power n plus 1 minus 1 upon n plus 1 is equal to c0x plus c1x square by 2 plus c2x cube by 3 and so on up to cnx to the power n plus 1 upon n plus 1. Then we write the expansion of x plus 1 to the power n and multiply these two equations and equate the coefficient of x to the power n plus 1. So similar to question 108 and quite easy. Question 110 says that we have to prove that C0 minus 2 square C1 plus 3 square C2 and up to minus 1 to the power n plus 1 whole square Cn is equal to 0 where n is greater than 2. So we have 1 minus x to the power n is equal to C0 minus C1x plus C2x square up to minus 1 to the power n Cnx to the power n. We multiply both sides with x. Then we differentiate with respect to x. We get 1 minus x to the power n minus nx times 1 minus x to the power n minus 1 is equal to C0 minus 2 C1x plus 3 C2x square, 3 times C2x square and so on up to minus 1 to the power n times n plus 1 times Cnx to the power n. We multiply again with x and differentiate with respect to x. We get 1 minus x to the power n minus nx times 1 minus x to the power n minus 1 minus 2nx 1 minus x to the power n minus 1 plus n times n minus 1 x square 1 minus x to the power n minus 2 is equal to C0 minus 2 square times C1x plus 3 square times C2x square and so on up to minus 1 to the power n plus 1 whole square Cnxn. We put x is equal to 0 to get right hand side as the series required on left hand side and left hand side over here it becomes 0. So with this we come to the end of question 110. I'll show you my website. So you come to ashtavakra.org and download algebra, trigonometry and geometry from these 3 links, 2nd, 3rd and 4th links. Note that when you download the PDF, the date mentioned here won't be there. So you need to add this date in the PDF and come back after 15 or 30 days to see if the date has changed. If the date has changed, you can download the PDF again and update the date. I cannot really put the date in the PDF itself because it will make all existing links invalid. Also note that there are lots of typing mistakes as you would have observed till now. So make sure that you read it carefully. Also, if you want to ask questions to me, you can click the H link and come to kundika.ashtavakra.org. Make a login here and you have tags for algebra, calculus, ordinate geometry, probability, trigonometry, and general mathematics tag is there. So use these tags to ask me questions to me, and I'll be more than happy to answer your question. So I thank you for watching the video, and we will meet again tomorrow with 10 more problems on permutation, binomials, theorems, expansion. So thanks a lot for watching the video. Stay curious, keep learning, and most importantly, enjoy. We will meet again tomorrow. Thank you.